One way to look at our latest implementation of Letrec is that we've taken some cycle that is expressed in terms of bindings. Here F effectively refers back to itself, and turned it into a cyclic data structure, where in our implementation of the same sort of expression we would end up with a closure that has an environment inside that has a binding of F back to the same closure. So this is really a cyclic data structure. You can think of the box as being something that's allocated, and that the value inside of here is an address that refers back to a place that holds the closure V in the store. I'd like to look a little bit more about at cyclic data structures. In PLAI typed, we could create a box that has some other box inside of it, and then we could set the box B to contain itself. Now this turns out not to work because of the type system. Basically, B wants a box, but it wants a box that has a number inside of it, and B is a box that has a number inside of it. So for a little bit, I'm going to change back to an untyped language, bracket, so that I can explore this a little bit more. So I don't need the extra layer of boxes. I'm just going to have a box B, and then I can set that box B to be inside of itself. If I look at B, what do I get? The way it prints out is this notation that has, remember that hash ampersand means box, and the value inside of that box is a #0 hash, which is a reference back to this definition, #0 equal. In other words, it's a box that refers back to itself. If I try to look inside the box B, then I get back just the same thing. No matter how many times I unbox, I get back to the same box because the content of the box is the box itself. An infinite chain of boxes like that is really not useful in any context. We can get a little closer to something useful by having a list involved. So what if I cons one onto, well, I could cons onto the empty list, and that just gives me a list containing 1. What if I cons onto a box that has nothing inside of it? What I get back now is not really a list. We would call this a pair. It's a pair of 1 and, the dot notation here means pair, a box containing false. And if I use list tail on L of 1, then I get back the second part of the pair, which is a box. If I take that box and set L inside of it, now let's look at L again. L is a list that contains 1, and then after that is a box that contains the lists back. So if I do list ref 0 to get the first item of that list, I get 1, and then if I do list tail 1, unbox that, then I get back to the same list that we had before. So this is almost like a list that is infinite, that has a 1 as the first item and a 1 as the second item, and so on, except that we have these boxes interleaved with things. So you may wonder, is there a way to make just a list that refers back to itself, where the list tail would be another list that you could list ref directly? And the answer is that you can construct one of those with a shared construct. So I can say shared is an L. Shared binds L in the same way as letrec. I'm going to say it's a list containing 1. Actually, I want to say it conses 1 onto the list L in the list L. And now you see we get back something that doesn't have any hash ampersands in it. It's a pair of 1 and a pair of 1 and a pair of 1. So let's define this thing to L on the outside. I can say list ref L0 to get a 1 back. If I say list tail L1, which drops the first thing off the list and gives me the rest, I get back the same thing as L. So that if I do a list ref on that, I get a 1 out. And because I have chains of pairs, I can do list ref L2 and get the third item in the list, conceptually, which is a 1. Or I can get the fourth item in the list, or I can get the 3001st item in the list, which is an L. So now we have an infinite list of 1s. So what was the difference between shared and Letrec? If I tried to do Letrec and look at the result, then I don't get this infinite list of ones. I get ones consed onto undefined. And so shared is an even more recursive form of binding than Letrec. It knows not only how to deal with things that are automatically delayed, like lambdas, it can also sort of arrange an appropriate delay for certain things like cons. But even shared can't do everything. For example, if I try to, instead of consing directly onto L, make a list out of L, and then pull the first thing back out of it, well, then it doesn't work again. Right? Even though that looks, taking the first of a list that I just made, looks just like using the thing that's in the list, that actually works. And what's going on here is that shared has to recognize certain patterns that it knows how to delay, and other patterns it doesn't recognize and doesn't know how to delay. So there's a continuum here from non-recursive bindings to recursive bindings that work with explicit delays to recursive bindings that work with some implicit delays. And you might wonder just how expressive you can make this, how you might more implicitly delay all expressions. And that will bring us to a lazy language next time.